Okay. Hi everyone. Yeah. So today I'm gonna talk about forecasting work that we're doing at UK Power Networks as part of the newly formed DSO, distribution system operator, which has been going for about a month now. Yeah, I think kind of similarly to the talk from Andrea, I think part of it's going to be hopefully a kind of practical overview of what we actually do and some of the problems that we face. Yeah, we're a new team, so there's lots of room for kind of engaging with research. There's kind of not too many sunk costs at this point, so hopefully we get some ideas from you how we should progress as well. So just briefly about UK Power Networks, for those who don't know. So we're the distribution network operator for the south east of England, so covering 3 of the DNO regions, including London. And we cover kind of a third of everything. So a third of homes and businesses, third of generation, the embedded generation, and a third of peak demand is in our regions. Now, we've recently formed the distribution system operator in April, DSO, and the goal of this is effectively to defer network reinforcement through the flexible use of the network. It's kind of like the overall objective. So traditionally, the DNOs have been responsible for operating and kind of managing the infrastructure, the physical infrastructure, creating the network and maintaining the network. However, for a number of reasons, which I'm sure you're all familiar with, like electrification, which is increasing demand, the increase in renewables generation, taking a more kind of active role in managing the network is now kind of essential. And on top of that, we now have the tools in terms of the technology and the sort of digitalization and our kind of view of the network to take much more of an active role in managing the network. So there are sort of 3 roles that the regulator Ofgem have laid out for us, which I think logically go planning and network development, then market development and network operation. So what I mean by that is, in the first role, we're taking a long-term view of where on our networks need to be reinforced or need to have flexible services in order to maintain reliable running of the network. So where do we anticipate to have congestion in the future? Then we look at those areas and we say, okay, where can we actually create a market, a flexibility market for people who have generation or demand that they can turn up or turn down to help us run the networks with greater stability. And then thirdly, we have people in the short term taking operational decisions on the network to dispatch that flexibility, i.e. determine when we're actually going to use it, potentially take kind of preemptive actions on the network to stabilize it, and of course, if there is a fault in the network, to actually fix it. So I'm part of the data science team, whose kind of core responsibility within the DSO is short-term forecasting. So I'll kind of go on to where that fits into the role of the DSO, but that's our core responsibility. We're sort of kind of a mix of backgrounds and expertise, so quite a lot of domain expertise. We've had people who've been in the company for a while as engineers with really strong power systems engineering backgrounds, and then we have people like myself who came from academia, and Jamie Bright, who leads the team, also from academia, who have much more of a background in kind of core kind of data science, machine learning, forecasting. And then we have a data engineer who does the really important stuff. But we have this kind of mixture of domain and forecasting expertise, which I think is really essential. And on top of that, we do a lot of work in the DSO more broadly in terms of just software, automation, education, helping people actually use data effectively, and many other roles as well, one of which is covered by the thing. Yeah, reporting and visualization. So we maintain a dashboard internally. So we maintain a dashboard internally that we can use to kind of monitor the data that we actually produce within the DSO. So this is a kind of diagram of what the control engineers see in the DSO. And I thought I'd show this because it kind of gives you a sense of when we're doing these short-term forecasts, when I'm talking about short-term forecasts, talking about roughly up to 2 weeks two weeks in advance. We could be forecasting basically any of the values on this network here. And one of the first things we do when we think a forecast is going wrong is we bring up this part of the network. We'll see what's going on in that part of the network in real time. And sometimes it may well be totally obvious why our forecasts are going wrong. It may be that there's an analog, so a measurement device, which is, misbehaving. Maybe that the network has been reconfigured, for instance, and that's, changing the way that electricity is flowing through the network and making things more difficult to forecast. It's really fascinating to just go through the network, and it's really, I feel fortunate that we're able to do it and just understand the complexity of the system we're dealing with. And, in the forecasting context, is something I'll come on to later on. But in the forecasting context, that's really important in terms of understanding that, that you have these are not just point values which do not relate to one another. They're often the aggregations of one another, or they relate very strongly to one another. And this is an example of one of the cases where this becomes a real issue. So this was a primary substation I just picked out yesterday, where at some point the configuration of the network was changed by someone in the control room. It may well have been that they were responding to a fault. So a fault in the network which meant that they needed to, essentially redirect flows within the network, and we get something like this going on. And that change is very, very difficult to predict. It's probably a fault. So get into this kind of zone of sort of fault prediction, or it may have been for other reasons, but ultimately a human decision resulted in this step change in the graph, which is very difficult for us to account for. So how does the sort of forecasting fit in, particularly short-term forecasting, fit into the role that the DSO has? I think before I go into that, I think one of the things which is not obvious to me, I came from an academic background, and people talked about the DSO and sort of more active, proactive management of distribution networks for a long time, and forecasting was, I think, seen as a real important enabler of that. I think when I then joined the DSO, there are certainly lots of use cases for short-term forecasting, but there are also many cases in which you do need to convince people that it's necessary. I think UKPN is certainly kind of very optimistic about the use of data and the kind of use of data science and having this kind of view of the network through short-term forecasting as improving network operations, but it's not obvious in all contexts. But these three, I think, are definitely cases where forecasting can be really, really useful and improve the efficiency in terms of our running of the network. So the first one is flexibility market. So as I say, the main role of the DSO is to defer us, increasing the capacity of the network to allow more generation or more demand to join the network. And one of the key parts of that is running a flexibility market or flexibility markets. In order for us to do that really efficiently, we really need to have a short-term view of how much flexibility, so how much flexibility we're going to need on, for instance, a day-ahead basis. That's one of the main kind of uses for short-term forecasts. The second reason is within the control room. So as I say, the people working in the control room are firstly deciding when they need to dispatch the flexibility. So we'll procure the flexibility quite a long time in advance in general, but then we will have to then decide when they're actually going to be used, and that's the role of the control engineers, and they will make those decisions based on forecasts. In addition, when a fault occurs in the network, these engineers have to make a decision about how to reconfigure the network, and that reconfiguration might last for quite a long time whilst the fault is being fixed. So as a result, they need to have a view over the next few days of what load is going to be on the network to understand if that change to the topology, to the configuration of the network, is actually going to cause another problem in 2 days' time. That's another very important kind of use case in the control room. And the third sort of major use case is for generators which are on connections, special kind of connections contracts where we're allowed to curtail them. So for context, it used to be that generators could connect to our networks and they would have unlimited capacity or unlimited sort of access to our network to generate. In order to sort of understand to increase our usage of the network, we now offer these connections called flexible connections, where the generator is allowed to connect sooner than they otherwise would have been able to, but they will accept some level of curtailment. We'll have some control such that in peak hours or may only be a few hours of the year, we're able to curtail them to stabilize the network. For those generators, they want to have a view of whether they're likely to be curtailed on, for instance, day ahead basis. So they can then decide what markets they can bid into, what flexibility services they can provide. So that's the kind of third use case, is providing forecasts of curtailment for those customers. So as you can see, obviously these are three big use cases. They're also quite specific use cases, and I think there's a lot of work that a lot of the work we do in short-term forecasting, we do have to find these use cases. It's not that these short-term forecasts fix every problem. They fix specific problems, albeit very important ones. So I just want to talk about sort of characteristics of what we're forecasting and what kind of short-term forecasting is like at UKPN. I think one of the main characteristics is that we forecast a lot of assets. So we've only been live with our forecasts for a couple of months. And our first deployment looked at just the GSPs on our network, which is around 60 sites. So these are the kind of entry points, the junctions with national grid, if you like, so with the transmission network. So that was 60 sites, which we were producing individual forecasts for. We then added another 70 in our sort of second deployment, which were for these curtailable connections. So for the constraints, which these flexible connections, which I was talking about before, the constraints which they're affected by, we're producing forecasts for them. I put that in a slightly lighter green because that's going through a kind of quality control phase, because they are much more difficult quantities to forecast, and we're not providing them to customers yet. We're not there. It's not public yet. But the grid supply points forecast we do provide to customers on our network. So that's roughly 130 sites, which is, in a lot of context, I think would already be quite a lot of values to be forecasting. But I've kind of included on there another sort of, various other assets we have on our network that we probably will want to forecast at some point, and that's at current levels. So many of these things, so for instance, storage, we're anticipating that to grow substantially. Solar PV, all of these sites are like those values. So in brackets is the number of assets we have currently on our network. They're all going to grow, and so you could easily see that we could easily be, say, 1,000 assets that we're forecasting. So the sort of scale of the number of values that we're forecasting is pretty large, I think. As a result, sort of our computational resources are really important, or computational limitations. That we can develop some fancy models, but training them for 1,000 different sites, potentially individually, is going to be really expensive. So one of the things that we're interested in general is, can we fit a single model for many different sites, which would reduce the maintenance costs and potentially the computational costs of actually keeping these forecasting models going. So that's something that I think we're interested in generally, and it'd be great to kind of engage with research community on that. Another sort of very important characteristic is that people, particularly within UKPN, are generally not interested in just seeing the curve. The curve is basically not important. What is really important is the curve can go over some kind of limit or get close to some kind of limit. So almost everything in forecasting has a limit. That's what we're interested in. So in general, that'll be some kind of firm capacity. So some capacity where we know the grid's going to be secure, so long as we remain below it. or for instance, in the case of these customers who we can curtail, it's if it exceeds this limit, is anyone going to get curtailed? As a result, they're also kind of related to that, I suppose. We often want to produce forecasts which are pretty conservative. So the sort of ideally a full probabilistic forecast is best, and we can set those levels. But if we don't have that, we want to add a significant amount of headroom, because decisions made on the grid, can have serious consequences if our forecasts are too optimistic. And then sort of finally, I think just a more general point is sort of within taking all this into account, marginal gains in accuracy are just not that important. Accuracy is usually a constraint, but it's not something that we're just continuously trying to improve. Often we're interested in increasing the number of sites that we're forecasting, or we may be interested in something which is accuracy but not mean squared error. We might be wanting to look at how often does our forecast for the maximum load at this site actually exceed, how often does it actually exceed our forecast. This is this is our grid supply point forecast, and this kind of summarizes some of the points we've been making. So these are the grid supply points that we're producing forecasts for at the moment, or most of them. There's one which doesn't have any kind of data on it. We have a bit of a data issue going on there, and there are a few other sites which don't appear. And the red dotted lines represent the minimum and the maximum that we're actually reporting to customers. So this is what we show to customers. And as you can see, we're adding quite a lot of headroom to our forecasts. But for kind of full disclosure, at the moment, this is a point forecast, and the headroom and the footroom that we're adding on is determined by historically what our errors have been. So we've looked at like diet. So within the day, we get a distribution or a sort of time series of actually a distribution of what our errors have been at that time of day. We use that to determine the headroom and the footroom. So this is not a full probabilistic forecast at the moment, but it does produce pretty conservative kind of bounds. I think it raises a kind of another kind of general characteristic, I would say, of forecasting the DSO, which is that I think there's sometimes tension between kind of producing these forecasts, which might be technically correct a lot of the time, i.e. like the demand or the load remains within the bounds that we've set, but actually aren't that useful because they are too conservative. So I think it's a balance that we often have to strike. Is how essentially it's essentially the level of conservatism. How right do we want to be versus how useful do we want to be? I think that's often the trade-off that we're kind of considering. This is sort of just a screenshot of the dashboard that we have internally. So this is a kind of forecast viewer that we have, and people in the company can go on. They can look up sites, and they can see the forecasts. And one of the things that people asked for was to be able to go back in time. They didn't want to just see today's forecast, and they didn't want to just see an error metric either. They want to be able to go back, visually see how correct our forecasts have been for the last, say, month, and use that kind of visual reference as, basically how much do I trust this forecast? How useful is this forecast? And this is developed with Plotly Dash. So this is kind of our internal forecast viewer. So the kind of benchmark forecast that we're using at the moment is a model we call analog ensemble. And the analog ensemble is quite it's a very effective forecasting model. It's pretty intuitive, but it works very well for quite a lot of sites, and at least as a benchmark, it's very effective. And I think that was the first thing we wanted to do with forecasting, was get a benchmark forecast in place for the sites that we want to forecast, and then think about developing models and comparing them with this benchmark. And so the principle of it is we go back in time, we look at similar periods to the recent history at the time of the forecast. So in this case, we're looking at 24 hours as our kind of window. We then look at the last year of data. We said following a period which looks like the last 24 hours, what then happened? By taking kind of a number of these analogs, we can then produce kind of like a mean estimate of what's going to be happening over the next few days. One of the nice things about this is that you can produce forecasts with a long horizon very easily. So you're not producing individual forecasts for each time horizon. You get a full forecast with basically the same computational cost. And this is our kind of benchmark model. But what we're kind of developing at the moment is a more general workflow for forecasting, or rather for selecting models that outperform our benchmark. I'll come on to that into the details in a sec. But I think one thing to note is that most of the time, what we're really trying to do is build wrappers around existing open source software, and that is the way that we feel like we can produce the most value and be the most efficient as forecaster at UKPN. So, we feel that the thing that we are uniquely able to do within UKPN as a data science team is integrate forecasting software into our own systems with our own data. We have access to the data that no one else has, and that's ultimately where we can add value. There's really not that efficient for us to be the ones developing, the core forecasting methods. We're hoping that we can get those things out of research, we can get those things out of open source. But what we need to do is build all the infrastructure around that to integrate our own data and actually run the forecasts. So our development generally focuses on integrating with our internal data, cleaning the data, making sure our forecasts are kind of are valid and we're prepared to give them to either control engineers or customers at UKPN. And then the aspect of model selection, so automating a lot of the process of adding a new asset to what we're forecasting. So overall, we kind of have this workflow in the bottom left. So for each of our, let's say, 100 assets, as an ongoing process, we're running a kind of model selection for each of those assets. So we look back to the last month, the last 3 months, and we simulate how we would have done with the different forecasters that we've developed or that we're using. That's good. Obviously, that's quite a computation expensive operation, so that's going on a kind of ongoing basis. Then every day, for the selected best models, whatever we decide is the best model for each asset, we will retrain that model if it needs to be retrained. So depending on the type of model, that might not be feasible. We might do it every week, we might do it every 2 weeks. That's kind of on a model dependent basis. And then we have the process that we run more frequently. So every day we produce this report. So that graph of the grid supply point forecast, we produce that every day, send that to customers. We analyze our errors and we use that to determine the headroom and the foot run. So that gets updated on a daily basis. And then every 30 minutes we produce a forecast which we then serve, have put it in various formats that we can then access for things like the reporting that we do to customers. That sort of workflow on the right just summarizes how this real-time 30-minute forecasting works. So the process of essentially taking each of those assets, looking up which model we've chosen as being the best for that asset, and then in a kind of vectorized format, batch format, initializing those models, running them for the tags that are relevant, and then concatenate those results to serve in whatever formats we need. So one of the things that kind of you may well be thinking is that, and that I mentioned at the beginning, is that how are we accounting for the kind of network effects within our forecasts, which is a very good question. So there's kind of levels to the extent at which you can do this. So at a simplified level, you can often account for these network effects using simple connectivity, kind of parent-child relationships between assets. And so that's something we're developing at the moment. Gathering data from all across the company to create this kind of tree on a grid supply point basis of how the network looks. So then we can say, okay, if the network topology changed slightly, then we can adjust that parent-child relationship and aggregate up from, say, our primary substations up to our grid substations or grid supply points. But what we're interested in doing on a longer term basis is actually integrating a power system network model into our forecasts. So we're supporting Fraunhofer Institute, who developed Panda Power, to essentially integrate with our network models. So a lot of our work goes on in terms of network planning. Use software called Power Factory. So we have network models, and people who've done distribution network planning or network planning may well be familiar with Power Factory. We essentially want to provide an interface into our Power Factory model with Panda Power, which will enable us, we think, to come up with much more kind of accurate forecasts, robust forecasts which obey the laws of physics, which would be good. And I think just generally build trust in our forecast. I think this is something that is really important, is that for control engineers who have not been using forecasts in the past and who really do understand the network extremely well, they need to have trust in our forecasts in order to use it to inform decisions in kind of live context. And I think having a kind of power flow simulator underlying our network is a really kind of important thing to do in that. So yeah, just to before I finish, there's a very short list of some of the questions that we sort of ask each other and think, wouldn't it be great if someone could answer that for us, because we don't always have the time to do it, and it's requires a lot of expertise. As I say, I think the first thing we're interested in is, given all these sites, given the fact that we want to expand this quite significantly, how effective can large models trained on multiple time series perform, and is that going to be in the long run better strategy? What we see in deep learning kind of suggests that larger models which can be trained on multiple time series in order to predict multiple time series may well be kind of a real kind of powerful route to forecast it, at least to accurate forecasts, but also potentially in terms of our maintenance of the models, a much easier thing to actually maintain. Second thing is we need to do a lot more work in accounting for these topological changes. Part of that is just data. Part of that is actually taking these decisions that control engineers are making them, feeding them into our network model, which we then feed in, which then supports our forecasting. But part of it, I think, is probably going to be a lot more complex than that, and I think it's going to be. I think that's an area of research which I think, so far as I can tell, needs to be addressed, particularly in the context of distribution networks. And then there are a few others. So, for instance, using our smart meter data, we have there's a lot of interest in monitoring on the network, and we don't monitor everything on the network, particularly at low voltage levels. And so we think that with everyone getting smart meter in their homes, can they basically do that monitoring for us? The fourth one is an interesting kind of question about. I talked about curtailment of assets. If we're forecasting curtailment, one of the things we've got a problem with is the fact that our training data includes the curtailment. So we're never going to forecast something which would exceed a limit, because the limit never gets exceeded. So we need to include that data somehow in our training data, retrain the model on that. And are there any risks in doing that? Can we do this kind of counterfactual analysis of what would have happened if they'd not been curtailed? And then finally, and this is hopefully something we'll be able to do with Panda Power, is integrating state estimation with forecasting. So state estimation, what that would allow us to do is to produce forecasts for parts of the network we don't even monitor, and will also improve the forecast accuracy of sites where we know we've got significant measurement errors. So where the analogs that we're getting from our measurement devices are known to be wrong by at least some of that. there are many more. This is a short list, but yeah, it would be really good if we could work with people on any of these questions. I think would be great. Yeah, thank you.